for the session, Jay. Jay is currently hustling in the quantum measurements and control group at TIFR as a part of his PhD journey. He is a footballer as well as the lead guitarist in our band, in the conduction band. And he is all about building and turbocharging those quantum processors to make them super efficient. Today, he's going to drop some knowledge bombs on us about the mind-blowing world of realizing quantum computers using electronic circuits that work at temperatures colder than his ex's heart. So let's hear it from Jay. Have to make it full screen, right?
Next slide before highlighting. Okay. This button for highlighting.
Yours is a PDF.
Yeah.
Okay. So let me just see. Next.
Click. Just click.
Yeah. Check. Thank you for the kind introduction. Am I audible to everyone? Okay. I'm Jay, and I'm currently working in the Quantum Measurements and Control Laboratory. And we work on trying to build quantum computers using some things called superconducting circuits. But before that, let's talk a little bit about the conventional computers that we are used to. Let's ask the question, like, how do computers work? So they are basically machines which do arithmetic really, really fast. So us humans, we are very familiar with numbers. We use these 10 digits, these 10 symbols to represent them. And then after 9, we say the next number is called 10 or 10. And then 11, 12, and so on. And this is called the decimal system. And we are all very familiar with this. Computers count in a similar way, but there's one fundamental difference. Instead of using 10 symbols, they just use 2 symbols. And they are 0 and 1. But it turns out that this doesn't fundamentally change anything. Like you can represent any quantity in the world in the same way. You just have to combine the 2 symbols in this particular way. So the first number is 0, then it's 1, then it's 10. This is analogous to us reaching 10 after 9, then 11. And then after 11, you directly have this 100, 101, and so on. And it turns out that computers can count like this. And moreover, they can define some operations on these binary numbers, and these are called logic gates. And this is similar to, just one second. Yeah. And this is similar to how we define operations on our numbers, which is addition and multiplication. And by combining these logic gates, even computers can do the same thing. They can add and they can multiply. And once you can multiply, you can do very, very complicated things like solve differential equations and things like that. And because of this, we can achieve really, really powerful computers. And that's the reason the powerful computer in your phone right now can run Instagram for you, for example. But we can ask this question, like, why binary? Like, why not stick to how humans count? That would be so much more natural. Well, it just turns out that it's easier to represent 2 states instead of 10 states, right? So, for example, a coin. You could use a coin to represent 0, like the heads to represent 0 and the tails to represent 1. Similarly, you can use a switch. The off state can represent 0 and the on state can represent 1. It would be really hard to build a switch with 10 different configurations. So it's just easier to do this. And how is it done in our computers? Like clearly our computers do not have a bunch of coins in them. It's done using these things called transistors. And the 0 state is represented by current not passing through this, and the 1 state is represented by current passing through this. And our CPUs are basically a bunch of these transistors all working together in tandem to perform these computations. Computers have really revolutionized the society we live in. I mean, we see its effect everywhere. The internet, we live in the age of information, and that has really transformed how the world looks. It has, in fact, really advanced the progress in science as well. I think we heard a talk by Koshwendra some time back where he was talking about using computer simulations to study galaxies, or stars rather. And so, in fact, that's true. And computers have been used as a very strong predictive tool. To give a kind of an easier example, are you all familiar with what this is? This is an LBW review in the cricket. So what happens here? The bowler delivers the ball, and the ball actually hits the player's leg instead. But we can use this to determine if the player was not there, would the ball have hit the wicket? And how is it done? We take the data of the initial trajectory of the ball, and then we encode the physics that the ball is following. And then given the position of the wickets, we can infer whether the ball would hit the wickets or not. So in this way, you can feed in the physics of the situation, and you can simulate what could happen in reality, and that could really tell us something which we cannot observe, but we can ask the computer what would have happened. And this simple idea has been used to extract information about a variety of systems, like all the way from cells to galaxies. But can our computers really simulate everything that exists in nature? Well, to our best understanding, it turns out that they may struggle at certain problems. So let's understand what kind of problems they are. Have you heard of atoms and molecules? So it turns out that these atoms and molecules, they do not follow the physics of cricket balls and cars. They follow some rules which are called the laws of quantum mechanics. And this is a slightly more, it's a slightly different theory which gives us predictions which are kind of different from what normal physics anticipates. And it turns out the computers struggle to simulate the laws of quantum mechanics on larger structures. One would ask, okay, why do we care if they can do this or not? We can think of a simple example, maybe in relation to the previous talk, that drug discovery. If you had a molecule and if you could understand the physics that the molecule follows, you could maybe simulate how this molecule would behave in certain different situations. And maybe you could do some sort of a quantum chemistry experiment, but not really an experiment, but you could simulate how the molecule behaves. But it turns out that even for nominal molecules of this size, our normal computers struggle to simulate them. And the simple reason is that they require too much memory, which means that they require too many bits. And this is related to the underlying mathematical structure of quantum mechanics. It's a bit hard to get into this, but you'll have to believe me when I say that our computers do struggle. Now, this was a problem, and actually this has implications even in advancement of science, like we would be interested in simulating other quantum systems. So scientists asked this question, like, what if we had a computer which itself functioned on the principles of quantum mechanics? And that is what I'm referring to as a quantum computer. And it turns out that they can exist, and we are trying to build them. Now, what are the building blocks required to build a quantum computer? Like the bits for a classical computer, or the computers that we are familiar with, quantum computers require things called qubits or quantum bits. And they are slightly more complicated mathematical objects. A normal bit that we just talked about can occupy only two of these states, like the 0 or the 1, like the transistor with the current not passing and the current passing. A qubit is a more complicated structure. You can visualize it like the globe. So if the north pole represents 0 and the south pole represents 1, our bit can be in only these two positions, but a quantum bit can be on any point of the sphere. So it can be a little bit 0 and a little bit 1 at the same time. And this is because the laws of quantum mechanics allow this. So we're going to use these quantum states to encode information instead of bits. Why this idea is powerful, maybe we can we can kind of understand using this example. So if we have 3 bits, what are the total number of combinations that we can have of this nature? Can anyone say? 8. What about with 4 bits? 2 raised to 4, that's correct. So if you have n bits, you will have 2 raised to n combinations. And so as the number of bits increase, you will have exponentially large number of combinations. But if all of your bits are classical, they can be only in one of these 2 to the power n states. However, if you have n qubits, then they can be simultaneously in all of these 2 to the power n states. And this is something which is referred to as quantum parallelism. So quantum computers kind of derive their power from this in some sense. So you can have n qubits, but they could be in all of these states at once. Okay, so this idea sounds neat, but how do we realize them? So you need some hardware which supports this preparation and manipulation of quantum systems. There are various candidates. So like bit was a concept, but you needed the transistor to actually build computers which are useful in today's life. So we are kind of in that part of the story where we're kind of looking for physical systems which will allow us to do this. And there are some candidates like neutral atoms, superconducting qubits, quantum dots. And I'm going to focus on this particular architecture, which our lab works on. So have you all heard of something called a pendulum? Are you familiar with it? A pendulum is nothing but a swing in the park, right? It's just a mass hanging by a thread, which is pivoted at some point. And what happens when you take this pendulum and take it in an extreme and then you leave it? It oscillates, correct. So when you take it to this point, you increase its potential energy. And therefore, it acquires some energy from the virtue of the gravitational field. And then when you leave it, it comes to this point and it becomes really, really fast. And it converts all of that potential energy to kinetic energy. And this way, it kind of oscillates, exchanging energy between kinetic and potential energy. But because of things like air resistance and friction, the amplitude of these oscillations damp, and over time, our pendulum comes to a standstill. Something very analogous can also be observed in electrical circuits. So think of this circuit, which are you all aware of things like inductors and capacitors? Have you studied them in school? Great. So inductors store energy within them in the form of currents. So if there's a current passing through the inductor, it'll store some energy. Contrary to that, if there is charge across a capacitor, that's how it will store energy. So if you put some charge on this capacitor and you close this switch, suddenly there'll be a potential difference, and the charge will kind of flow in the form of a current through this inductor. And much like how the potential energy was getting slowly converted to kinetic energy, that will start to happen from the static charge being converted to currents. And at some point, all of the energy from the capacitor will be stored in the inductor, and this process will again keep on happening. But in the same way, like the air resistance was there in the previous case, if this resistor will act, will play the same role, and it will dissipate energy slowly till all of your oscillations come to a standstill. But what will happen if you put these circuits, if you subject these circuits to really, really low temperatures? It turns out that if we build these circuits in a particular way and we cool them down, we can achieve something called superconductivity, and this allows dissipation-free oscillations. What this means is that now you have purely a capacitor and an inductor. And this allows for long lifetimes of oscillations, which means that your oscillations will now no longer experience the damping, and they can go on for very, very long times. And because they're at such low temperatures, we'll talk about what I mean by low. They will show some quantum effects, which I will also describe in the next slide. And because of these long lifetimes, we will also be able to observe these quantum effects. Now, have you heard of atoms and molecules? Sure you have. And have you heard of energy levels of an atom? So the physicists in the previous century were perplexed because it turns out that atoms had very fixed quantized energy levels. Did you study that in school by any chance? Okay. So in much the same way, when you put these circuits at really low temperatures, it turns out that they occupy very specific and quantized energy levels. And what we will do is we will use this lowest energy state, which means that our oscillator has no energy at all, to encode our state 0. And this lowest, the next to the lowest energy state, which means our oscillator has the minimum possible energy, and use that to encode the one state. And this will form our qubit, the last two energy levels of our system. Now, there are two requirements for achieving or observing these quantum effects. So if the same circuit is at room temperature, we do not observe any of this. And that's because all of these energy levels are populated by thermal fluctuations, or they're already populated by particles simply because the circuit is at 300 Kelvin. So if we study the energy difference between these two levels, there's a temperature associated with that energy, and it turns out to be 240 millikelvin. To give you a scale, the temperature of outer space is around 4 Kelvin. So this would be around 10 times colder than outer space. And we in fact have to go to a temperature which is 10 times lower than this, so something like 0.01 Kelvin. So we have to go to a temperature which is 100 times colder than outer space in order to achieve these effects. And we can in fact do this in our labs. To do this, we use something called a dilution refrigerator. This is like the fridge that you use to keep your food cold, but it's a lot better and it's a lot more expensive. To give you a scale, this one of these costs about 5 crore rupees. And yeah, that's a lot. And that's not sufficient actually. So these are the different plates which represent the different temperatures that the fridge is at. And this base plate, which is at around 10 millikelvin, that is where our experiment lies. And we mount our cavity onto this. So this is actually the circuit, which was represented in the last slide. These are two metallic pads, and this represents the capacitance between the two pads. And this small thing you see in the middle is actually the inductor. To give you a scale, this is 200 microns, and this is like hundreds of nanometer. So yeah, these things are small, but definitely not as small as atoms and molecules, and they are still able to show quantum effects. And because the experimenter lies outside, they have to be connected through cables all the way to equipment which is in the lab, which is at room temperature. And so we have to take care of many things to ensure that the quantumness of this system is not disturbed. So we use various cryogenic filters and shieldings and many of these fancy things. But what's important is that we are able to observe quantum effects, which are typically only observed in atoms and molecules, in chips of sizes which you can hold in your hand. And I think that's pretty fascinating. Now, once you have these quantum states, you can actually manipulate them. You can shine light, which is of the same energy as the transition between these two levels. And you can manipulate the state of the qubit. So you remember a slide in which I showed the globe with the 0 representing as one of, let's say, the South Pole and the 1 being at North Pole. So you can make your qubit you can prepare your qubit in all of these states by shining light of appropriate energies. And you can prepare them in these even superposition states. And this is some data taken in a lab where you can think of these three curves as the x, y, and z coordinates of this vector on this sphere. And you can see that as time passes, you can see some very controlled oscillations on this sphere. So it turns out that yes, you can manipulate these quantum states. Furthermore, what you can do is you can couple many of these circuits to each other, and you can make multiple qubits interact with each other and work together. So this would be similar to how your CPU has many, many transistors working with each other to perform calculations which are heavy. You can now put many of these circuits together and form things called quantum processors, where you can address problems which are of like a higher dimensionality. For example, simulating the molecule that we are interested in. And there have been some proof of principle experiments. So currently we're at a stage where our quantum computers are not as powerful as we want them to be, but we have been able to simulate the physics of these small molecules such as the hydrogen atom, the H2 molecule and the LiH molecule, and we have been able to correctly predict the energy landscape. Moreover, there have been some quantum advantage-like experiments. So these are problems which are presumably hard for the normal computers to solve, and they have been solved by some of the quantum processors that we have. But these problems do not have real-life significance. So they're again a proof of principle, but we are making very strong progress, and we will soon hopefully achieve, maybe in the next decade, a quantum computer which can solve some real-life problems for us. We, the Quantum Measurements and Control Laboratory, also work on quantum phenomena in these superconducting circuits. We work on improving the efficiency of these quantum processors. So for example, if you have many of these qubits, we are trying to enhance how many of these qubits can be connected to other. So the calculations performed on such a processor will be faster as compared to the conventional processors. And we have also worked on this aspect where we are exploring some more complicated circuits to do similar things. And this is some work done by a previous PhD student, Tanay. And this was one of the first results in quantum computing in this field in our country, where he demonstrated a 3-qubit algorithm on this circuit. With that, I would like to thank the members of my lab who have been instrumental in all of this work. And I hope you guys got a flavor of what this field is about. And just to end the talk, I would like to show you a small reel I made for my Instagram. And I'm very proud of it. So I would want to show all of you that. Just tell me if you like it. Let me first mute.
Do you want sound?
I will experiment with that. Okay. Okay. There's no sound, unfortunately, but this is the chips I was talking about. They are fabricated in the clean room, and this is similar to the techniques used in how normal computers are built, the CPUs. And these qubits are now then placed, and this is us mounting those qubits onto the base plate of the dilution fridge that we showed. And then this is all the complex wiring and the filtration. And eventually we have to put all of these scans to protect our experiments from the surrounding radiation. And all of these steps are necessary to, ensure that the quantumness of these qubits is preserved. And once this is closed up, we need to set up the equipment outside the fridge, which will synthesize all of these pulses, which will let us manipulate the quantum state. And this is how we observe the quantum mechanics on chips that you can hold in your hand. Thank you.
Thank you, Jay. Now the stage is open for questions. Yeah.
I guess going back to the slides.
Yes.
Good evening. So how do you make gates with these circuits like Hadamard gate or the XYZ gates?
Okay, great question. Let me just open my slides.
Sure.
Yeah. So basically, you can, firstly, when you cool down the system, you can measure the energy difference between the 0 state and the 1 state. So you can precisely calculate the energy difference here. The next thing you can do is you can shine photons, which is of the same energy as this difference. And what this leads to is coherent oscillations of this qubit state on the Bloch sphere. So this is the sphere which is representing the quantum state. And you can imagine that this point has 3 coordinates, x, y, z, and they represent where it is on the sphere. And here you can see that we are able to manipulate exactly what these coordinates are by changing for how long we shine our pulse. And so we can stop at any point. For example, if you were interested in the Hadamard gate, you would want to you'd want to turn 0 into this state. So you can precisely calibrate your pulse so that the Hadamard gate is performed.
One more question. So can you go to the next slide where you show entangled qubit? Yeah, why do you use a capacitor there? Is there any reason why
Well, it's kind of easy to do. You can keep 2 of these chips close to each other. So by virtue of being close to each other, there'll be some capacitive coupling with each other. But you're right. I mean, there's no fundamental reason to do this. You can have inductive coupling as well. This is just an example I chose.
So to take your analogy from, let's say, using base 2 to base 10, it makes arithmetics easier for us. Quantum computing adds just to say more base or higher base in whichever arithmetic what you want to do. What I'm trying to ask is, how do I, let's say, mathematically add 2 plus 3 in quantum computing, right? Representing bits or qubits. This very simple addition.
Okay.
With binary, we can know, with transistors and all that, how that works actually. But here in qubits, how do you actually do, let's say, 2 plus, or even represent 2, for example?
Okay. So I'll make one comment before that. So I'm not claiming that quantum computers will replace all of the conventional computers. So quantum computers will be better at solving some specialized tasks which are inaccessible to conventional computers. So you can imagine it as computing branching out. So you will always need your normal computers to perform tasks, and quantum computers cannot outperform them in all of those. So to do 2 plus 3, you will actually never use a quantum computer. You will use your standard computer. But moving on to your question, I think you said that this is like adding, like changing the base. But that's not true. So here also we are using only 2 symbols, 0 and 1. You're actually fundamentally changing how you're storing information. So in the bit, you only allowed it to be in 2 states, 0 and 1. But here you're allowing more possibilities mathematically. But you are still going to use the same 2 symbols to represent numbers. So your 2 is still going to look like 1, 0, even in this case. So you can use the same mapping to represent numbers even for quantum computers. And you will actually never use a quantum computer to do these tasks which your normal computers are good at already.
Why are LC circuits only used in quantum computers? Because it gives sustained oscillations, right?
Right.
But then it won't attain stability, no? At any stage, at t equals to infinity.
Oh, so actually, we would like it if they don't achieve stability, because achieving stability is like losing energy, right? You put it in an oscillatory state, and then we actually work really hard at trying to maintain these oscillations.
Yeah.
And what you're actually doing is that you're, you are using these 2 states to represent 0 and 1. So you are using the stable state where there's no oscillations to represent 0. And you are using the state in which it is doing these oscillations with the minimum possible amplitude to represent 1. And now, because the laws of quantum mechanics allow it, our quantum pendulum can be in these 2 states, like a combination of these 2. But when we want it to be in 1, that is when you want it to have these oscillations, you would actually like it that it remains there till the time we ask it to stop. So that's why we're actually very happy with the fact that it doesn't stop by itself.
Thank you.
I'm sorry, one more question. So while doing measurement, you're basically forcing it to one state, right? While doing a measurement operation on a qubit, so you will force it to be stability, right? If I'm not wrong.
Yeah, I mean, so you will project it onto one of these states, but it can be either 0 or 1. So we will stop it only if you measure 0. You may project it to 1 as well. So
I had a question. So, like, what is the qubit? Like, what actually is it? Is it like a fundamental particle, like a proton, electron, or?
no, it's just a way to represent information. So a bit is like conceptually it's nothing, right? I mean, you imagine a transistor because we are using a transistor to represent 0 or 1, but a bit is just an idea that you can use these 2 symbols. So in the same way, a qubit is the fundamental unit of quantum information.
You reach about 4 Kelvin in the experiment, right? In the
Sorry?
you reach your refrigeration reaches about 4 Kelvin. So
10 millikelvin.
oh, sorry, 10 milli. Yeah. So
Yeah.
what is the like, how do you reach those temperatures?
Okay, that's a great question. So we use this idea called, so it's called a dilution refrigerator because of the process it uses. So I'll give you a brief analogy. So at this point, I've said this too many times, but have you ever cooled down your hot tea?
I mean, by blowing, yes, but
Yeah, by blowing over it.
Yes.
So what you're doing is you're disturbing the vapor pressure on top. And because of that, there's air which is dissolved in your tea, which comes up to maintain, kind of achieve that equilibrium again. And as it does that, it takes some energy away from the tea and cools it down. So what we do here is we have a mixture of helium-3 and helium-4, and we continuously pump out helium-3, which disturbs the vapor pressure on top of this mixture. And to maintain that, the helium-3, which is mixed inside the helium-4, it comes out and in that process, it cools down your mix a little bit. And then we take this and pump it back in, and we do this in a closed cycle. And everything which is connected, thermally connected to this mixture, also cools down to such low temperatures. And if you engineer these ratios and quantities correctly, you can achieve such low temperatures.
Thank you.
Sorry, I still can't wrap my head around what is the qubit, what the question he asked.
Okay.
So can I imagine it like a decimal number between 0 and 1 and representing every possible number between 0 and 1 at the same time? Or you're trying to say that there are chances of having qubit being close to 0.99999 and or whenever it's going to represent 0, its chances of being closer to 0.000001. Am I imagining this correct or understanding?
No, so okay, I'll give you an example of an entity which is not a qubit, but maybe it has some similarities. So when you toss a coin and it's mid-flight, there's a certain probability that it's 0, and there's a certain probability that it's 1. So when I ask you the question, like what state is the coin in, you will say, I mean, it's possible that it's this. I mean, there's a certain probability that it's 0, and there's a certain probability that it's 1. So you will characterize the state of the coin as something which is 0 and something which is 1. Now you replace these with not probabilities, but something called complex numbers, and that mathematically is a qubit. So the closest thing maybe in our real life, which we can see around us, is maybe a flipped coin mid-flight is a qubit. Yeah.
Any more questions? Okay, so let's give it up for Jay once again.
Thank you.